Imagine, if you will, a star so colossal that it makes our sun look like a mere speck in the cosmic ocean. We're talking about stars that are not just big, but absolutely monstrous, with some reaching sizes so vast that if one were to replace our sun, it would swallow up Mercury, Venus, Earth, Mars, and even the asteroid belt, stretching out to nearly the orbit of Jupiter. These are the blue supergiants and hypergiants, the heavyweight champions of the stellar world. But what makes these giants so rare, and why are they so crucial to understanding the life and death of stars? Stick around, because we're about to dive into the fascinating, the explosive, and the downright mind-boggling world of these celestial titans. The birth of blue supergiants and hypergiants. In the vast cosmic nursery of nebulae, where clouds of gas and dust swirl and coalesce, the most massive and luminous stars begin their dramatic lives. Blue supergiants and hypergiants are born from these stellar cradles, their formation a testament to the extreme conditions required to create such behemoths. These stars are rare, with blue supergiants making up only a tiny fraction of the stellar population and hypergiants even rarer. Their birth is a high-stakes cosmic event, akin to the formation of a supermassive black hole, but with a spectacular display of light and energy. The process starts with a molecular cloud, a dense region of gas and dust. For a blue supergiant or hypergiant to form, the cloud must be exceptionally massive and turbulent. Gravity pulls the material together, creating a protostar at the core. As the protostar grows, it heats up, and nuclear fusion ignites, marking the birth of a new star. The most massive stars, those that will become blue supergiants and hypergiants, form from the densest and most turbulent regions of these clouds. Their formation is rapid and intense, like a cosmic explosion in slow motion. These stars are not just large, they are extraordinarily luminous. A blue supergiant can be hundreds of thousands of times brighter than our sun, and a hypergiant can be millions of times brighter. Their immense energy output is a result of their massive size and the intense nuclear reactions in their cores. The sheer scale of these stars is hard to comprehend. If you were to replace our sun with a blue supergiant, it would extend far beyond the orbit of Mercury, possibly even reaching the orbit of Venus. Hypergiants are even larger, some stretching beyond the orbit of Mars. The rarity of these stars is a result of their short lifespans. They burn through their nuclear fuel at an astonishing rate, living fast and dying young in cosmic terms. This rapid evolution means that, at any given time, there are relatively few blue supergiants and hypergiants in the universe. Their dramatic lives and explosive deaths make them some of the most fascinating objects in the cosmos. From their birth in the turbulent hearts of nebulae to their spectacular ends as supernovae, blue supergiants and hypergiants are among the most awe-inspiring sights in the night sky. Stellar classification: O and B types. In the vast canvas of the cosmos, stars come in a dazzling array of sizes and colors, but none command as much awe as the blue supergiants and hypergiants. These stellar titans, classified as O and B types, are the heavyweight champions of the universe, pushing the boundaries of size, luminosity, and rarity. Picture a star so massive that if it were placed in our solar system, its outer layers would extend beyond the orbit of Jupiter. That's the scale we're talking about. These stars are not just big, they're extraordinarily rare. In our Milky Way galaxy, which boasts an estimated 100-400 billion stars, only a handful of these giants exist. Their scarcity is a testament to their fleeting existence, as they burn through their nuclear fuel at a prodigious rate, living fast and dying young in cosmic terms. O-type stars, the rarest and most massive of the bunch, are the rock stars of the stellar world. They are incredibly hot, with surface temperatures ranging from 30 to 50 Kelvin. To put that into perspective, our sun's surface temperature is a mere 500 Kelvin. O-type stars are also incredibly luminous, emitting energy at a rate millions of times greater than our sun. Their intense radiation and stellar winds sculpt the interstellar medium, triggering star formation and leaving an indelible mark on their surroundings. B-type stars, while less extreme than their O-type counterparts, are still formidable. They have surface temperatures ranging from 10 to 30 Kelvin and luminosities thousands of times greater than our Sun together. O and B types represent the pinnacle of stellar evolution, their immense power and rarity, making them objects of fascination for astronomers. The sheer scale and power of these stars are almost incomprehensible. Consider Rigel, the brightest star in the constellation Orion, and a blue supergiant of spectral type B8ia. It's about 860 light-years away, yet it's visible to the naked eye. That's like seeing a candle flame from hundreds of miles away. Rigel's radius is about 79 times that of our Sun, and it's about 120 times more luminous. If Rigel were placed in our solar system, it would be so bright that it would cast shadows on Neptune. These stars are not just points of light. They are colossal nuclear furnaces, forging heavy elements in their cores and scattering them into the universe when they eventually explode as supernovae. Their deaths are as spectacular as their lives, seeding the cosmos with the building blocks of planets and life. Yet, for all their grandeur, blue supergiants and hypergiants are ephemeral. Their immense mass and luminosity mean they burn through their nuclear fuel at a staggering rate. While our Sun has a lifespan of about 10 billion years, these stars may only live for a few million years. It's a cosmic blink of an eye. Their rarity and short lifespans make them precious targets for astronomers. Studying these stars provides insights into the early universe, when massive stars were more common, and the processes that drive stellar evolution and nucleosynthesis. They are the celestial equivalent of a supercar, powerful and impressive, but with a limited fuel tank. Their existence reminds us of the dynamic and ever-changing nature of the universe, where even the most massive and luminous stars are transient features on the cosmic landscape. What defines a supergiant? Supergiants are among the most massive and luminous stars in the universe. They are categorized based on their spectral type and luminosity class. What sets them apart is their sheer size and brightness. These stars are typically 10 to 70 times more massive than our Sun and can be hundreds to thousands of times larger in radius. Their luminosity can be hundreds of thousands to millions of times greater than that of the Sun's supergiants are rare, making up only a tiny fraction of the stars in the Milky Way. Their short lifespans, ranging from a few million to tens of millions of years, contribute to their rarity. This is because massive stars burn through their nuclear fuel much faster than smaller stars. To put their scale into perspective, if a supergiant like Rigel were placed in our solar system, it would extend beyond the orbit of Mars. Their immense size and energy output make them easy to spot, even from great distances. Supergiants are often found in young star clusters and associations, where star formation is still active. They play a crucial role in the evolution of galaxies, enriching the interstellar medium with heavy elements through stellar winds and supernova explosions. Their rarity and short lifespans make them fascinating objects of study for astronomers. The classification of supergiants is based on their spectral type and luminosity. They are divided into two main groups: blue supergiants and red supergiants. Blue supergiants are hotter and more luminous, with surface temperatures ranging from 10 to 50 Kelvin. They are typically younger and more massive than red supergiants. Red supergiants, on the other hand, are cooler and more evolved, with surface temperatures ranging from 500 to 500 Kelvin. They are often the final stage in the evolution of massive stars before they explode as supernovae. The transition from blue to red supergiant status is a complex process influenced by various factors, including mass loss and internal nuclear reactions. What defines a hypergiant? Hypergiants are the titans of the stellar world, pushing the boundaries of what we understand about stars. These celestial behemoths are incredibly rare, with only a handful known to exist in our galaxy. Their sheer size and luminosity make them stand out. But what truly defines a hypergiant is their extreme scale and the unique phases they undergo. Hypergiants are stars that have reached the upper echelon of stellar classification, often found in the topmost regions of the Hertzsprung-Russell diagram. They are typically more than 100 times the size of our Sun and can be 1,000,000 times more luminous. Their immense energy output and instability set them apart from other stars, making them some of the most spectacular and short-lived objects in the universe. The rarity of hypergiants is a testament to their extreme nature. Stars of this magnitude are born from the most massive and luminous stars, which themselves are uncommon. Hypergiants represent the final, dramatic stages of these massive stars' lives. Their immense size and energy output make them highly unstable. They often undergo violent eruptions and mass loss, shedding material into space in spectacular displays. This instability is a defining characteristic, as it sets them apart from more stable, albeit still massive, blue supergiants. The sheer scale of a hypergiant's eruptions can be compared to the energy released by entire supernovae, albeit on a smaller scale. These eruptions are not just spectacular, they are crucial in understanding the life cycles of the most massive stars. To grasp the enormity of hypergiants, consider this. If a hypergiant were placed at the center of our solar system, its outer layers would extend beyond the orbit of Jupiter. Their size is so vast that they defy easy comprehension. The energy they radiate is similarly immense, with some hypergiants outshining entire galaxies. This luminosity is a direct result of their massive size and the intense nuclear reactions occurring in their cores. The sheer scale of these stars makes them visible from vast distances, even though they are incredibly rare. Their rarity is a double-edged sword. While it makes them difficult to study, it also underscores their importance in the grand tapestry of the universe. Hypergiants are the cosmic heavyweights, and their brief, fiery lives offer a glimpse into the extreme conditions that shape the evolution of the most massive stars. The life cycle of a massive star. In the vast theater of the cosmos, blue supergiants and hypergiants command attention. These are not your average stars. They are the heavyweight champions of the stellar world, boasting masses dozens of times greater than our Sun. Their lifespans are short, intense, and spectacular, akin to a cosmic firework that burns bright and fast. Born from the collapse of massive molecular clouds, these stars ignite nuclear fusion in their cores, fusing hydrogen into helium at a furious pace. This process generates immense energy, making them appear blue and shine with a brilliance that can outstrip entire galaxies. The rarity of these stars is akin to finding a diamond in a coal mine. In our Milky Way galaxy, which houses an estimated 100-400 billion stars, only a handful of blue supergiants and hypergiants exist. Their scarcity is a testament to their fleeting existence. These stars burn through their nuclear fuel at an astonishing rate, living fast and dying young. To put this into perspective, while our Sun has a lifespan of about 10 billion years, a blue supergiant might only shine for a few million years. It's like comparing a marathon runner to a sprinter. Both are athletes, but their paces and durations are vastly different. As these massive stars evolve, they undergo dramatic changes. Blue supergiants can swell into red supergiants, expanding to sizes that would engulf entire solar systems. This transformation is akin to a caterpillar turning into a butterfly, but on a scale that defies imagination. The final act of their life cycle is equally spectacular. When they exhaust their nuclear fuel, they collapse under their own gravity and explode in a supernova, one of the most energetic events in the universe. This cataclysmic event scatters heavy elements into space, seeding the cosmos with the building blocks for new stars and planets. It's a cycle of creation and destruction that underscores the dynamic nature of the universe. From main sequence to supergiant. Stars, those colossal nuclear furnaces scattered across the cosmos, lead fascinating lives. Their journeys are marked by dramatic transformations, none more spectacular than the evolution from main sequence stars to blue supergiants and hypergiants. This transition is a high-stakes game of stellar evolution, where only the most massive stars get a backstage pass. Main sequence stars, like our Sun, are the cosmic equivalent of the steady, reliable workers. They spend most of their lives in a stable state, fusing hydrogen into helium in their cores. But for stars with masses exceeding 8 times that of the Sun, the story takes a dramatic turn. These heavyweights burn through their hydrogen fuel at a prodigious rate, their cores simmering under immense pressures and temperatures. It's like comparing a small campfire to a roaring bonfire. The difference in scale is staggering. As these massive stars exhaust their hydrogen, they begin to fuse heavier elements, starting with helium. This shift triggers a series of changes that cause the star to expand and brighten, transforming it into a blue supergiant. Picture a star that was once a modest, steady burner, now swelling into a titan, its outer layers puffing up like a balloon. The star's surface temperature drops slightly, shifting its color from blue to a more subdued hue, but its luminosity skyrockets. Blue supergiants are rare, like finding a diamond in a coal mine. Their immense size and brightness make them stand out, but their lifespans are short compared to smaller stars. They are the rock stars of the universe, living fast, shining bright, and leaving a lasting impression. For the most massive stars, the journey doesn't end at blue supergiant status. Some continue to evolve into hypergiants, the true heavyweight champions of the stellar world. Hypergiants are even rarer than blue supergiants, with only a handful known in our galaxy. These stars are so massive and luminous that they push the boundaries of stellar physics. Their sheer size and energy output make them unstable, with violent outbursts and massive ejections of material. It's like watching a volatile, unpredictable force of nature, capable of both awe-inspiring beauty and devastating power. The transition from main sequence to hypergiant is a testament to the extreme conditions that can exist in the universe, where stars push the limits of what's possible. The journey from main sequence to supergiant and hypergiant is a dramatic tale of stellar evolution. It's a story of immense pressures, extreme temperatures, and the relentless fusion of elements. These stars, though rare, play a crucial role in the cosmos. They forge the heavy elements that make up planets, life, and everything we know. Their explosive deaths as supernovae scatter these elements across the galaxy, seeding the next generation of stars and planets. In the grand tapestry of the universe, blue supergiants and hypergiants are the threads that weave the story of creation and destruction, a cycle that has been repeating for billions of years. The role of nuclear fusion. In the vast cosmic ocean, blue supergiants and hypergiants stand as titans, their immense size and luminosity a testament to the incredible power of nuclear fusion. These stars, though rare, play a pivotal role in the universe's evolution. Nuclear fusion, the process that powers these stellar behemoths, is a high-stakes game of pressure and temperature. In the cores of these stars, hydrogen atoms are squeezed and heated to such extremes that they fuse into helium, releasing a tremendous amount of energy. This energy is what makes these stars shine so brightly, outshining our sun by hundreds of thousands, even millions of times. The scale of this fusion is staggering, like comparing a candle to a nuclear explosion. Yet, this process is not just about brightness. It's a cosmic alchemy that forges the elements necessary for life. The rarity of blue supergiants and hypergiants adds to their mystique. They are the rock stars of the universe, living fast and dying young. Their immense size and energy output mean they burn through their nuclear fuel at a prodigious rate. This rapid consumption leads to a relatively short lifespan, making them a fleeting spectacle in the cosmic ballet. Their rarity is akin to finding a diamond in a coal mine, a testament to the unique conditions required for their formation. These stars are often found in active star-forming regions, where the raw materials for their creation are abundant. Their presence is a sign of a dynamic and active stellar nursery, a place where the universe is constantly renewing and reinventing itself. The role of nuclear fusion in these stars is not just about energy production. It's a complex dance of elements, a symphony of creation and destruction. As the star ages, the fusion process shifts from hydrogen to heavier elements like helium, carbon, and oxygen. Each stage of fusion releases energy, but it also builds up the core of the star, increasing its density and temperature. This process continues until the star reaches the limit of its fusion capabilities, culminating in a spectacular supernova explosion. The energy released in this final act is so immense that it can outshine entire galaxies, scattering the newly forged elements into the cosmos. These elements become the building blocks for new stars, planets, and even life itself. Thus, the role of nuclear fusion in blue supergiants and hypergiants is not just about powering these stellar giants. It's about seeding the universe with the ingredients for creation. The HR diagram, mapping stellar evolution. In the vast canvas of the cosmos, stars come in a staggering variety of sizes, colors, and stages of life. To make sense of this diversity, astronomers use a powerful tool called the Hertzsprung-Russell (HR) diagram. This diagram is a scatter plot that maps stars based on their luminosity or absolute magnitude against their effective temperature. It's like a stellar family tree, showing the evolution of stars from birth to death. On this diagram, blue supergiants and hypergiants stand out as the rare, massive, and extremely luminous giants of the stellar world. Blue supergiants and hypergiants are among the rarest and most extreme stars in the universe. They are the heavyweight champions of the stellar arena, with masses ranging from tens to over 100 times that of our Sun. Their luminosity is equally staggering, with some hypergiants shining with the brilliance of several million suns. To put this into perspective, if you were to replace our Sun with a hypergiant, it would be so bright that it would cast shadows even at night, and its heat would scorch the Earth from millions of miles away. These stars are so rare that in our entire Milky Way galaxy, there are only a handful of known hypergiants. The HR diagram reveals the life cycle of stars, and blue supergiants and hypergiants occupy a brief but spectacular phase in this cycle. They are the final, dramatic act in the life of a massive star. Born from clouds of gas and dust, these stars burn through their nuclear fuel at an astonishing rate. Their immense mass creates intense pressure and heat in their cores, causing them to fuse heavier and heavier elements. This process is like a cosmic race against time, as the star's core gradually builds up layers of elements until it can no longer sustain nuclear fusion. The star then explodes in a supernova, leaving behind a neutron star or black hole. This entire process, from birth to supernova, can take just a few million years, a blink of an eye in cosmic terms. The position of a star on the HR diagram tells a story of its evolution. Blue supergiants and hypergiants are found in the upper left corner of the diagram, indicating that they are hot, massive, and extremely luminous. As they evolve, they move across the diagram, cooling and expanding as they fuse heavier elements. This journey is marked by periods of instability, with some stars undergoing massive eruptions or losing material through powerful stellar winds. These events can cause the star to temporarily change its position on the HR diagram, adding to the complexity and richness of stellar evolution. The HR diagram is not just a map, it's a dynamic snapshot of the ever-changing cosmos. Blue supergiants, characteristics, and traits. Blue supergiants are among the most massive and luminous stars in the universe. These celestial giants are typically more than 10 times the mass of our Sun and can be up to 1,000,000 times brighter. Their immense size and energy output make them stand out in the night sky, even from vast distances. Blue supergiants are relatively rare, given their short lifespans compared to smaller stars. They burn through their nuclear fuel at an astonishing rate, leading to a dramatic and often explosive end. Their rarity and sheer scale make them objects of fascination for astronomers and stargazers alike. The characteristics of blue supergiants are as striking as their appearance. These stars are incredibly hot, with surface temperatures ranging from 20 to 50 Kelvin. This intense heat gives them their distinctive blue hue, which is a visual testament to their extreme energy output. Blue supergiants are also known for their powerful stellar winds, which can eject massive amounts of material into space. These winds are so strong that they can shape the surrounding interstellar medium, creating intricate nebulae and influencing the formation of new stars. Their immense gravity and radiation pressure make them dynamic and ever-changing entities. One of the most intriguing traits of blue supergiants is their instability. Despite their massive size, these stars are prone to violent outbursts and eruptions. Some blue supergiants undergo periodic pulsations, causing their brightness to fluctuate dramatically. Others experience catastrophic explosions, known as supernovae, which can outshine entire galaxies for a brief period. These explosive events are not only spectacular, but also play a crucial role in the recycling of matter in the universe. The elements ejected during a supernova enrich the interstellar medium, providing the raw materials for new stars and planets. In this way, blue supergiants are both destroyers and creators, shaping the cosmos in profound ways. The rarity of blue supergiants adds to their allure. Given their short lifespans, these stars are relatively few in number compared to smaller, more stable stars like our Sun. Their brief but brilliant existence makes them a fleeting spectacle in the cosmos. Astronomers often refer to them as the rock stars of the universe, given their dramatic lives and explosive ends. Their study provides valuable insights into the life cycles of massive stars and the processes that drive stellar evolution. Understanding blue supergiants helps us unravel the mysteries of the universe and appreciate the dynamic nature of the cosmos. Hypergiants, the extreme end of the spectrum. Hypergiants are the colossal titans of the stellar world, pushing the boundaries of what we understand about stars. These are the most massive and luminous stars known, dwarfing even the mighty blue supergiants. Hypergiants are incredibly rare, with only a handful known in our galaxy. Their sheer size and energy output are almost incomprehensible. To put it into perspective, if you were to replace the Sun with a hypergiant, it would extend far beyond the orbit of Mars, engulfing Mercury, Venus, Earth, and Mars in its fiery embrace. Their luminosity is equally staggering, with some hypergiants shining millions of times brighter than the Sun. This immense energy output is a double-edged sword, as it accelerates their evolution and ultimately leads to their dramatic demise. The scale of hypergiants is truly mind-boggling. Their radii can range from 100 to over 500 times that of the Sun. To visualize this, consider that the Sun is already so large that over 1 million Earths could fit inside it. Now, imagine a star so vast that it could swallow entire solar systems. Hypergiants are not just big, they are unstable. They undergo violent outbursts and mass loss, shedding material into space at incredible rates. This instability is a hallmark of their extreme nature, a testament to the chaotic forces at play within these stellar behemoths. Their rarity is a direct consequence of their extreme properties. Stars of this magnitude are born from the densest and most massive molecular clouds, and their lifespans are relatively short compared to smaller stars. Hypergiants are classified based on their spectral type and luminosity class. The most well-known hypergiants are the blue and red hypergiants. Blue hypergiants are hotter and more luminous, with surface temperatures exceeding 20 Kelvin. They are the rarest and most extreme of all hypergiants. Red hypergiants, while cooler, are still incredibly luminous and have radii that can reach over 500 times that of the Sun. These stars are in the final stages of their evolution, and their fate is sealed. They will eventually explode as supernovae, leaving behind either a neutron star or a black hole. The energy released in these explosions is so immense that it can outshine entire galaxies for a brief period. The study of hypergiants is crucial for understanding the life cycles of massive stars. Their extreme properties provide insights into the processes that govern stellar evolution. Hypergiants are also important for their role in enriching the interstellar medium with heavy elements. Through their violent outbursts and eventual supernova explosions, they distribute these elements across the galaxy, seeding the next generation of stars and planets. In a sense, hypergiants are the cosmic alchemists, transforming the primordial elements into the building blocks of life. Their rarity and extreme nature make them fascinating subjects for astronomers, offering a glimpse into the most dramatic and powerful events in the universe. Luminosity, the brightness of blue supergiants and hypergiants. Blue supergiants and hypergiants are among the most luminous stars in the universe. Their brightness is so intense that it's hard to comprehend. To put it into perspective, consider our Sun, which is a relatively modest star. If you were to replace the Sun with a blue supergiant like Rigel, the brightest star in the constellation Orion, the light would be blinding. Rigel shines with a luminosity about 120 times greater than our Sun. That's like swapping a 60-watt bulb for a 7.2 megawatt one. The sheer scale is staggering. These stars are not just bright, they are incredibly rare. In our Milky Way galaxy, which contains an estimated 100-400 billion stars, only a few thousand are blue supergiants. Hypergiants are even rarer, with only a handful known to exist. Their scarcity is a testament to their extreme nature. They burn through their nuclear fuel at an astonishing rate, living fast and dying young in cosmic terms. The luminosity of these stars is a direct result of their massive size and high temperatures. Blue supergiants and hypergiants have surface temperatures ranging from 20 to 50 Kelvin, making them appear blue or blue-white. Their immense size means they have a vast surface area from which to radiate energy. To visualize this, think of a blue supergiant as a giant light bulb. The larger the bulb, the more light it can emit. A blue supergiant like Rigel has a radius about 79 times that of the Sun. If you were to place Rigel at the center of our solar system, its surface would extend beyond the orbit of Mercury. The sheer volume of light they emit is mind-boggling. For instance, the hypergiant Eta Carinae is so luminous that it's visible from Earth despite being over 7,500 light-years away. Its brightness varies dramatically, sometimes outshining entire galaxies. The rarity of these stars is closely tied to their luminosity. Stars like blue supergiants and hypergiants are in a transient phase of stellar evolution. They are the final, fleeting stages of massive stars before they explode as supernovae. Their extreme brightness is a double-edged sword. While it makes them spectacular to observe, it also means they burn through their fuel rapidly. This rapid burn leads to their short lifespans, making them rare. To put it into perspective, a blue supergiant might live for only a few million years, while a star like our Sun can shine for about 10 billion years. The hypergiants are even more extreme. Stars like Eta Carinae are so massive and luminous that they are on the verge of stability. They are constantly battling the forces of gravity and radiation, making them unpredictable and fascinating objects of study. Their rarity and luminosity make them invaluable for astronomers seeking to understand the life cycles of stars and the dynamics of the universe. Temperature, the heat of these stellar giants. Blue supergiants and hypergiants are among the most massive and luminous stars in the universe. Their temperatures are staggering, often ranging from 20 to 50 Kelvin. To put that into perspective, our Sun's surface temperature is a mere 500 Kelvin. These stellar giants are not just hot, they are infernos compared to most other stars. Their intense heat is a direct result of their massive size and the nuclear fusion processes happening in their cores. The sheer scale of their energy output is akin to millions of suns combined, making them some of the most powerful objects in the cosmos. The rarity of these stars adds to their mystique. Blue supergiants and hypergiants are incredibly uncommon, primarily because their lifespans are relatively short on a cosmic scale. They burn through their nuclear fuel at an astonishing rate, leading to a rapid and often explosive end. Their short lives and high energy output make them rare gems in the vast expanse of the universe. Think of them as the supercars of the stellar world, powerful, fast, and not something you see every day. Their scarcity is a testament to their extreme nature, making each one a unique and fascinating object of study. The heat of these stars is not just a number, it's a defining characteristic that shapes their behavior and appearance. Blue supergiants and hypergiants emit most of their light in the ultraviolet spectrum, which is invisible to the human eye. This means that despite their immense brightness, they often appear fainter than cooler, redder stars when viewed through optical telescopes. Their high temperatures also drive powerful stellar winds, which can eject massive amounts of material into space. These winds are so strong that they can create intricate nebulae around the stars, adding to their dramatic presence in the night sky. The sheer force of these winds can be compared to a hurricane on Earth, but on a scale that dwarfs anything we experience on our planet. Understanding the temperature of blue supergiants and hypergiants is crucial for astronomers. It provides insights into their life cycles, their impact on the surrounding interstellar medium, and their role in the evolution of galaxies. These stars are not just hot, they are dynamic and ever-changing, with temperatures that can fluctuate due to various factors, including their stage of evolution and any ongoing stellar activity. Their heat is a driving force behind many of the phenomena we observe in the universe, from the formation of new stars to the enrichment of the cosmos with heavy elements. In many ways, these stellar giants are the architects of the universe, shaping the cosmos with their immense energy and heat. Size, comparing to our Sun. In the vast canvas of the cosmos, blue supergiants and hypergiants stand as colossal brushstrokes, their sheer size dwarfing our Sun in a manner that's almost incomprehensible. Our Sun, a humble yellow dwarf, has a radius of about 696,340 kilometers. Now, picture this: a blue supergiant like Rigel, one of the most luminous stars in our night sky, boasts a radius roughly 79 times that of our Sun. That's a mind-boggling 55 million kilometers, making it so large that it could engulf the orbit of Mercury and still have room to spare. Hypergiants, the even more massive cousins, can have radii hundreds of times larger than our Sun. The star VY Canis Majoris, a red hypergiant, is estimated to have a radius between 1,301 540 times that of our Sun. To put that into perspective, if our Sun were a small marble, VY Canis Majoris would be a sphere as wide as a small neighborhood. The scale of these stars is not just impressive, it's downright mind-bending. Consider this: if you were to replace our Sun with a blue supergiant like Rigel, its outer layers would extend far beyond the orbit of Mercury, possibly even reaching the orbit of Venus. The sheer volume of these stars is equally staggering. A single blue supergiant could contain millions of suns. Imagine a vast, empty stadium. Now, fill it with millions of identical marbles. That's the kind of volume we're talking about. Hypergiants take this to an even more extreme level. Their sheer size and mass make them some of the rarest and most short-lived stars in the universe. They burn through their nuclear fuel at an astonishing rate, living fast and dying young in cosmic terms. The rarity of these stars adds to their allure. Blue supergiants are relatively uncommon, and hypergiants are even rarer. In our entire Milky Way galaxy, there are only a handful of known hypergiants. Their short lifespans, combined with their massive size, make them a fleeting spectacle in the grand tapestry of the cosmos. They are the rock stars of the universe, living life in the fast lane and burning out quickly. Their immense size and luminosity make them easy to spot, even from vast distances. They shine brightly, casting a blue or red hue depending on their temperature, and dominate their surroundings with their sheer presence. Yet, their rarity means that we don't often get to witness their dramatic lives and explosive deaths. Mass, the heavyweights of the universe. In the vast cosmic arena, blue supergiants and hypergiants stand as titans, their masses dwarfing that of our Sun by staggering margins. These celestial heavyweights tip the scales at a mind-boggling 10 to 100 times the Sun's mass. To put that into perspective, if the Sun were a humble 100-pound weightlifter, a blue supergiant would be a 0 to 10 pound sumo wrestler. Their sheer size is almost incomprehensible, with diameters reaching hundreds of times that of our Sun. Picture a star so large that if it were placed at the center of our solar system, it would engulf everything up to the orbit of Mars or even beyond. The rarity of these stars is as striking as their mass. They are the cosmic equivalent of finding a diamond in a coal mine. In our Milky Way galaxy, which boasts an estimated 100-400 billion stars, only a few thousand blue supergiants and hypergiants exist. Their fleeting lifespans, measured in mere millions of years compared to the Sun's 10 billion-year lifespan, contribute to their scarcity. These stars burn through their nuclear fuel at a prodigious rate, living fast and dying young in spectacular supernova explosions. Their rarity and immense mass make them the rock stars of the universe, captivating astronomers with their brilliance and power. The scale of these stars is not just a matter of size, but also of influence. Their immense gravity and radiation output shape their surroundings, creating vast cavities in the interstellar medium and triggering the formation of new stars. They are the cosmic architects, sculpting the galaxies around them. Yet, their very mass is a double-edged sword. While it grants them their immense power and luminosity, it also seals their fate. The more massive a star, the shorter its lifespan, as the intense gravitational forces compress the core, increasing the rate of nuclear fusion. This relentless burning leads to a rapid exhaustion of fuel, culminating in a cataclysmic supernova. In the grand tapestry of the universe, blue supergiants and hypergiants are the brief, brilliant brushstrokes that leave an indelible mark. Stellar winds, the powerful outflows. Blue supergiants and hypergiants are among the most colossal and energetic stars in the universe. Their sheer size and luminosity are awe-inspiring, but what truly sets them apart is the sheer power of their stellar winds. These winds are not gentle breezes, but rather torrential outflows of charged particles and radiation, hurtling into space at mind-boggling speeds. The scale of these winds is difficult to comprehend. A single blue supergiant can lose mass at a rate equivalent to the entire Earth's mass every few thousand years. Hypergiants, being even more extreme, can shed mass at rates thousands of times higher. This loss is not a slow, steady process, but a violent, dynamic one, driven by the star's intense radiation and magnetic fields. The winds from these stars are so powerful that they can shape the very fabric of their surroundings. They carve out vast cavities in the interstellar medium, creating stunning nebulae that glow with the light of the stars within. These winds also play a crucial role in the life cycle of galaxies, enriching the interstellar medium with heavy elements forged in the star's core. Without these winds, the universe as we know it would be a very different place. The energy carried by these winds is staggering. A single blue supergiant can release more energy in its winds than the sun will in its entire lifetime. This energy drives shock waves that compress gas and dust, triggering the formation of new stars. It's a cosmic cycle of birth and death, where the demise of one star can spark the creation of many others. The rarity of these stars adds to their mystique. Blue supergiants and hypergiants are fleeting phenomena in the cosmic timeline. They burn through their fuel at an astonishing rate, living fast and dying young. Their rarity makes them precious targets for astronomers seeking to understand the extremes of stellar evolution. The winds from these stars are not uniform. They vary in strength and composition, influenced by the star's magnetic fields and rotational speed. Some winds are smooth and steady, while others are turbulent and erratic. This variability adds another layer of complexity to the study of these celestial giants. The winds can also interact with nearby companions, creating intricate dances of gravity and magnetism. These interactions can lead to the formation of spectacular phenomena like colliding winds and accretion disks, further enriching the cosmic tapestry. Spectral analysis, understanding their composition. Blue supergiants and hypergiants are among the most massive and luminous stars in the universe. Their sheer size and energy output make them rare, with only a handful known in our galaxy. These stars are not just larger versions of our Sun. They are entirely different beasts, with surface temperatures exceeding 20 Kelvin and luminosities millions of times greater. Their rarity is akin to finding a diamond in a coal mine, making each discovery a significant event in the astronomical community. Spectral analysis is the key to understanding the composition of these celestial giants. By examining the light emitted by these stars, astronomers can decipher the elements present in their atmospheres. Blue supergiants and hypergiants are primarily composed of hydrogen and helium, much like other stars, but their spectra reveal a rich tapestry of heavier elements. These elements are forged in the intense nuclear furnaces within the stars and brought to the surface through powerful stellar winds and convective processes. The presence of these elements provides clues about the star's age, evolution, and eventual fate. The spectra of these stars are complex and varied, reflecting their dynamic nature. Blue supergiants often exhibit strong hydrogen and helium lines, along with traces of heavier elements like carbon, nitrogen, and oxygen. Hypergiants, being even more massive and luminous, can show more pronounced features of these heavier elements. The intensity and width of these spectral lines can vary, indicating the star's temperature, gravity, and rotational velocity. For instance, a broadened line might suggest rapid rotation or strong stellar winds, while a narrow line could indicate a more stable atmosphere. Understanding the composition of blue supergiants and hypergiants is not just an academic exercise. It has practical implications for our understanding of the universe. These stars play a crucial role in the chemical enrichment of galaxies, dispersing heavy elements into the interstellar medium through stellar winds and supernova explosions. This process seeds the galaxy with the raw materials for new stars and planets, including the elements essential for life. By studying these stars, astronomers gain insights into the life cycles of massive stars and the evolution of galaxies. The rarity of these stars adds a sense of urgency and excitement to their study, as each one offers a unique window into the cosmos. The instability strip, pulsations, and variability. In the vast cosmic ocean, blue supergiants and hypergiants are the titans, their sizes and luminosities dwarfing our sun by staggering margins. These celestial behemoths, though rare, play a pivotal role in the universe's drama. Their lives are short, dramatic, and often end in spectacular supernovae. But before their grand finale, they exhibit fascinating behaviors, particularly in a region known as the instability strip. The instability strip is a narrow band on the Hertzsprung-Russell diagram where stars experience pulsations and variability. It's like a cosmic roller coaster, where stars expand and contract, their brightness waxing and waning. For blue supergiants and hypergiants, this strip is a hotbed of activity. Their pulsations can be so intense that they eject massive amounts of material into space, creating stunning nebulae. These eruptions are akin to a star's version of a volcanic explosion, reshaping their surroundings and seeding the interstellar medium with heavy elements. The scale of these pulsations is mind-boggling. A single pulse can cause a star to expand by millions of kilometers, its surface temperature dropping as it does so. This variability is not just a surface phenomenon. It's a deep-seated instability that ripples through the star's layers. It's like watching a colossal, slow-motion heartbeat, a rhythm that's visible across vast cosmic distances. The rarity of these stars makes their study a challenge, but each observation offers a treasure trove of data, a glimpse into the lives of these stellar giants. The instability strip is not a static place. It shifts and changes, influenced by the star's internal processes and external environment. For blue supergiants and hypergiants, this strip is a crucible of transformation. Their pulsations can trigger complex feedback loops, altering their evolution and potentially accelerating their journey towards the supernova stage. It's a dance on the edge of stability, a delicate balance between creation and destruction. Understanding this dance is key to unraveling the mysteries of these massive stars and their role in the universe's grand design. Eta Carinae, a notable example of a hypergiant. In the vast canvas of the cosmos, stars come in all sizes, but none are as awe-inspiring as the blue supergiants and hypergiants. These are the heavyweight champions of the stellar world, with masses ranging from tens to over 100 times that of our sun. Their sheer size is almost incomprehensible. If you were to place a hypergiant like Eta Carinae at the center of our solar system, its outer layers would extend beyond the orbit of Jupiter. That's a star so large that it dwarfs the sun into insignificance, a tiny speck in comparison. The rarity of these stars is as striking as their size. They are the celestial equivalent of a diamond in the rough, extremely uncommon and found only in specific regions of galaxies, often in the bustling stellar nurseries where star formation is at its peak. Blue supergiants and hypergiants are not just big, they are also incredibly bright and hot. Their surfaces can reach temperatures of over 20 Kelvin, making them appear blue-white in color. This intense heat and luminosity come at a cost. These stars burn through their nuclear fuel at an astonishing rate, living fast and dying young. While our sun has a lifespan of around 10 billion years, a hypergiant like Eta Carinae might only last a few million years. It's a cosmic blink of an eye, a fleeting moment in the grand timeline of the universe. Their short lifespans make them even rarer, as they are constantly evolving and changing, often ending their lives in spectacular supernova explosions. Eta Carinae, a notable example of a hypergiant, is a stellar drama queen. Located in the constellation Carinae, it is one of the most massive and luminous stars known. Eta Carinae is a true cosmic heavyweight, with a mass estimated to be over 100 times that of the Sun. Its luminosity is equally impressive, shining with the light of several million suns. This star is not just big and bright, it's also unstable. Eta Carinae is known for its dramatic outbursts, the most famous of which occurred in the 19th century when it briefly became the second brightest star in the night sky. These outbursts are thought to be caused by the star's intense stellar winds and instabilities in its core. Eta Carinae is a star on the edge, a celestial tightrope walker that could collapse into a supernova at any moment. The study of blue supergiants and hypergiants like Eta Carinae is crucial for understanding the life cycles of stars. These massive stars play a significant role in the evolution of galaxies, enriching the interstellar medium with heavy elements forged in their cores. They are the cosmic alchemists, transmuting simple hydrogen and helium into the building blocks of planets and life. Their explosive deaths as supernovae can trigger the formation of new stars, continuing the cycle of stellar birth and death. In many ways, these stars are the architects of the universe, shaping the cosmos with their immense energy and mass. They are a reminder of the dynamic and ever-changing nature of the universe, a testament to the incredible forces at work in the cosmos. Rigel, a prominent blue supergiant. In the vast canvas of the night sky, Rigel stands out as a beacon of stellar grandeur. This blue supergiant, located in the constellation Orion, is a true titan among stars. With a mass estimated to be around 20 times that of our Sun and a radius about 79 times larger, Rigel is a colossal entity. Its luminosity is staggering, shining with the brilliance of around 120 times that of our Sun. To put this into perspective, if Rigel were placed in the center of our solar system, its outer layers would extend past the orbit of Mercury, engulfing the tiny planet in its fiery embrace. Blue supergiants like Rigel are rare, occupying a brief but spectacular phase in the life cycle of massive stars. They burn through their nuclear fuel at an astonishing rate, leading to a relatively short lifespan compared to smaller stars. Rigel's intense radiation and powerful stellar winds create a dynamic and turbulent environment. These winds, composed of charged particles, stream outwards at velocities exceeding 30 kilometers per second, shaping the star's surroundings and influencing the interstellar medium. The sheer scale and energy of these processes make blue supergiants like Rigel some of the most dramatic and influential objects in the universe. The rarity of blue supergiants adds to their allure. They are the celestial equivalent of a fleeting meteor, a brief but brilliant display in the cosmic tapestry. Rigel's prominence in the night sky is a testament to its size and luminosity, making it a favorite among amateur astronomers and stargazers. Its blue hue, a result of its high surface temperature, sets it apart from the more common yellow and red stars. This color, combined with its brightness, makes Rigel a striking sight, even from light-polluted urban areas. The star's name itself, derived from the Arabic word for foot, reflects its position in the constellation Orion, where it marks the hunter's left foot. Rigel's impact extends beyond its visual splendor. As a blue supergiant, it plays a crucial role in the chemical enrichment of the galaxy. Through processes like stellar winds and, eventually, supernova explosions, Rigel disperses heavy elements into the interstellar medium. These elements, forged in the star's core, become the building blocks for new stars, planets, and even life. In this way, Rigel and its kin are the cosmic alchemists, transforming the simplest elements into the complex materials that make up the universe. The study of blue supergiants like Rigel provides valuable insights into stellar evolution, nucleosynthesis, and the life cycle of massive stars. Their rarity and short lifespans make them a fascinating subject for astronomers, offering a glimpse into the dynamic and ever-changing nature of the cosmos. The role of rotation, how spin affects evolution. Blue supergiants and hypergiants are among the most massive and luminous stars in the universe. These celestial giants can be tens of times more massive than our Sun and millions of times brighter. Their immense size and energy output make them rare, with only a few thousand estimated to exist in the Milky Way galaxy. The rarity of these stars is akin to finding a needle in a cosmic haystack, making each discovery a significant event for astronomers. The spin of these colossal stars plays a pivotal role in their evolution. Rotation affects everything from their internal structure to their eventual fate. When a blue supergiant or hypergiant spins rapidly, it can flatten its shape, creating a bulge at the equator. This is similar to how a spinning top widens at its middle due to centrifugal force. The faster the spin, the more pronounced this effect becomes. This rotational flattening can influence the star's magnetic fields, temperature distribution, and even the way it sheds material into space. Rapid rotation can also lead to the formation of stellar winds that blast outwards at incredible speeds. These winds can carry away massive amounts of material, shaping the star's evolution and potentially leading to the formation of spectacular nebulae. The winds can also interact with the surrounding interstellar medium, creating shockwaves that trigger the formation of new stars. This process is like a cosmic domino effect, where the death of one star can lead to the birth of many others. Moreover, the spin of these stars can affect their internal mixing processes. In slower spinning stars, convection currents mix the star's material more evenly. However, in rapidly rotating stars, these currents can be disrupted, leading to uneven distribution of elements. This can alter the star's chemical composition, temperature, and luminosity. For instance, a rapidly rotating blue supergiant might have a higher concentration of helium at its core, accelerating its evolution and potentially leading to a more dramatic end, such as a supernova explosion. The stress and rarity of these stars make their study a high-stakes game, where each observation can reveal new insights into the life and death of the universe's most massive objects. Magnetic fields, influencing stellar behavior. In the vast cosmic ocean, blue supergiants and hypergiants stand as titans, their immense size and energy output dwarfing that of our Sun. These stars, though rare, play a pivotal role in shaping their galactic neighborhoods. Their magnetic fields, often millions of times stronger than Earth's, exert a profound influence on their behavior and evolution. These fields are not static. They twist, tangle, and interact with the stellar wind, creating a dynamic and complex environment. Picture a star with a magnetic field so strong it can trap and accelerate particles to near-light speeds. This isn't science fiction. It's the reality for many blue supergiants and hypergiants. The magnetic fields of these stars can be so intense that they can even influence the flow of matter in their immediate vicinity. They act like cosmic lighthouses, guiding and shaping the stellar wind into intricate patterns. This wind, composed of charged particles, is deflected and funneled along the magnetic field lines, creating spectacular phenomena like stellar winds and magnetic towers. The rarity of these stars makes their study all the more fascinating. Blue supergiants and hypergiants are like the celebrities of the stellar world, drawing attention due to their scarcity and dramatic behavior. Their magnetic fields can cause them to rotate more slowly than their non-magnetic counterparts, a phenomenon known as magnetic braking. This is akin to a figure skater extending their arms to slow down during a spin. The magnetic field acts like an extended arm, sapping the star's rotational energy and slowing it down over time. These magnetic fields also play a crucial role in the star's evolution. They can channel matter away from the star's poles, creating massive, high-speed jets. These jets can interact with the surrounding interstellar medium, creating shockwaves and heating the gas. This process can trigger the formation of new stars, making blue supergiants and hypergiants not just influential in their own right, but also in the creation of new celestial bodies. Their magnetic fields, though invisible, leave an indelible mark on the cosmos, a testament to their power and influence. Binary systems, interactions, and effects. In the vast cosmic ballet, blue supergiants and hypergiants often find themselves in binary systems, dancing with another star in a gravitational tango. These systems are not just common, they're downright ubiquitous, with estimates suggesting that over half of all massive stars, like our blue behemoths, have at least one companion. The interactions in these systems can be as dramatic as they are consequential, shaping the evolution of the stars involved. Picture a cosmic game of tug-of-war, where the gravitational pull of one star can strip material from its companion, creating a stellar wind that's as fierce as it is mesmerizing. The effects of these interactions are profound and varied. In some cases, the mass transfer can trigger a burst of nuclear fusion, causing the receiving star to brighten dramatically. This phenomenon, known as a mass transfer event, can be likened to a cosmic refueling, where one star siphons off the resources of its companion to fuel its own luminosity. In other instances, the interaction can lead to the formation of a common envelope, where the two stars become enveloped in a shared atmosphere. This is akin to two dancers getting so close that their movements become intertwined, their individual identities blurring into a single, chaotic whirl. The rarity of these interactions is matched only by their scale. Blue supergiants and hypergiants are among the rarest stars in the universe, their immense size and luminosity making them stand out like cosmic lighthouses. When they engage in binary interactions, the effects can be cataclysmic, leading to phenomena like supernovae or even the formation of exotic objects like neutron stars or black holes. The sheer scale of these events is hard to fathom, with energies involved that dwarf even the most powerful human-made explosions. It's a stark reminder of the raw, untamed power that lurks in the depths of space. Yet, for all their rarity and drama, these interactions are a crucial part of stellar evolution. They shape the lives and deaths of stars, influencing everything from their chemical composition to their ultimate fate. In some cases, the interactions can even lead to the formation of new stars, as the ejected material coalesces into protostellar disks. It's a cycle of creation and destruction that's as old as the universe itself, a testament to the enduring dance of gravity and matter. So, the next time you gaze up at the night sky, remember that you're witnessing a cosmic ballet, where even the rarest and most massive stars are bound together in an eternal gravitational waltz. Supernova progenitors, the fate of blue supergiants and hypergiants. Blue supergiants and hypergiants are among the most massive and luminous stars in the universe. These celestial titans, with masses ranging from tens to over 100 times that of our Sun, burn through their nuclear fuel at an astonishing rate. Their immense energy output makes them appear incredibly bright, even at vast distances. However, their brilliance is fleeting. These stars are on the fast track to destruction, their lives measured in mere millions of years, a blink of an eye in cosmic terms. Their ultimate fate is often a spectacular supernova, a cataclysmic explosion that can outshine entire galaxies. The rarity of these stars is as striking as their size. In our Milky Way galaxy, which contains an estimated 100-400 billion stars, only a handful of blue supergiants and hypergiants are known. Their scarcity is a testament to their short lifespans and the specific conditions required for their formation. To put their scale into perspective, if our Sun were the size of a grapefruit, a blue supergiant would be as large as a small house. Hypergiants, the even more massive cousins, could dwarf a football field. Their immense size and energy output create a dramatic and dynamic environment, with powerful stellar winds and intense radiation. When a blue supergiant or hypergiant reaches the end of its life, it doesn't go quietly. The core collapses, triggering a runaway nuclear reaction that tears the star apart in a supernova explosion. This event is so powerful that it can briefly outshine the entire galaxy in which it occurs. The explosion scatters the star's outer layers into space, enriching the interstellar medium with heavy elements crucial for the formation of new stars and planets. The core itself may collapse into a neutron star, or, in the most extreme cases, a black hole. These remnants are invisible to the naked eye, but can be detected through their gravitational effects or emissions in other wavelengths, such as 10th rays. The study of blue supergiants and hypergiants provides valuable insights into the life cycles of massive stars and the dynamics of stellar evolution. Their rarity and short lifespans make them challenging to observe, but their dramatic deaths offer a unique opportunity to understand the processes that shape our universe. By studying these celestial giants, astronomers can piece together the puzzle of stellar evolution, from the birth of stars and nebulae to their explosive demise as supernovae. The information gleaned from these studies not only deepens our understanding of the cosmos, but also highlights the transient and dynamic nature of the universe we inhabit. Gamma-ray bursts, the most violent endings. In the vast cosmic theater, blue supergiants and hypergiants are the titans, stars that push the boundaries of size and luminosity. These celestial behemoths are incredibly rare, with hypergiants being the rarest of all, numbering only a handful in our galaxy. Their sheer scale is almost incomprehensible. If placed at the center of our solar system, their surfaces would extend beyond the orbit of Jupiter, engulfing Mercury, Venus, Earth, and Mars in their fiery embrace. Their luminosity is equally staggering, outshining our sun by millions of times. Yet, their lives are as dramatic as their size, often ending in spectacular fashion. One of the most cataclysmic endings for these massive stars is the gamma ray burst, GRB. GRBs are the most violent and energetic events in the universe since the Big Bang. They are intense flashes of gamma rays that last from a few milliseconds to several minutes. The energy released in a few seconds is equivalent to what our sun will emit over its entire lifespan. There are two main types of GRBs, long duration and short duration. Long duration GRBs, lasting more than 2 seconds, are often associated with the collapse of a rapidly rotating, massive star, like a blue supergiant or hypergiant, into a black hole. Short-duration GRBs, lasting less than 2 seconds, are thought to be caused by the merger of two neutron stars or a neutron star and a black hole. The process leading to a long-duration GRB is a cosmic ballet of extreme physics. As the massive star runs out of fuel, its core collapses under its own gravity, forming a black hole. The infalling material forms a rapidly rotating disk around the black hole, and powerful jets of plasma are ejected along the rotational axis. These jets, moving at nearly the speed of light, produce the intense gamma-ray emission. The energy scale is mind-boggling. A typical GRB releases more energy in a few seconds than our sun will in its entire 10 billion-year lifetime. The jets can be so powerful that they can disrupt the star's outer layers, leading to a supernova explosion. The resulting display is a cosmic fireworks show, visible across vast distances. The rarity of GRBs is a testament to the infrequency of such extreme events. They occur roughly once per day in the observable universe, but their randomness and brevity make them challenging to study. Yet, their study is crucial for understanding the life cycles of massive stars and the formation of black holes. GRBs are also of interest because they can provide insights into the early universe. The gamma rays travel vast distances, and their detection can help astronomers probe the conditions of the universe when it was much younger. Moreover, the afterglows of GRBs, which can last for days or even weeks, provide a wealth of information about the surrounding environment and the host galaxy. In essence, GRBs are not just spectacular ends to massive stars. They are cosmic lighthouses that illuminate the mysteries of the universe. The impact on surrounding space, nebulas, and star formation. Blue supergiants and hypergiants are among the most massive and luminous stars in the universe. These celestial titans, with masses ranging from tens to over 100 times that of our sun, exert a profound influence on their surroundings. Their immense energy output and powerful stellar winds shape the interstellar medium, triggering the formation of new stars and sculpting vast nebulae. The sheer scale of their impact is akin to a cosmic sculptor, chiseling away at the fabric of space to create intricate and breathtaking structures. The intense radiation and stellar winds from these giants ionize and push away the surrounding gas and dust, creating vast cavities known as H-second regions. These regions are often the birthplaces of new stars, as the compressed gas and dust can collapse under gravity to form protostars. The process is not gentle. It's more like a celestial storm, where the winds of these massive stars stir up the interstellar medium, causing it to clump and collapse. This star formation is not uniform, but rather occurs in fits and starts, much like a turbulent sea where waves crash and recede in an endless dance. The most dramatic examples of this phenomenon are the giant H-second regions, like the Tarantula Nebula in the Large Magellanic Cloud. Here, the radiation and winds from a cluster of blue supergiants and hypergiants have carved out a vast cavity, illuminating the surrounding gas in a spectacular display of light and color. The energy from these stars is so intense that it can trigger the formation of new stars at a rate hundreds or even thousands of times greater than in quieter regions of the galaxy. It's a cosmic feedback loop where the death of old stars fuels the birth of new ones. However, the influence of blue supergiants and hypergiants is not always beneficial. Their powerful winds and intense radiation can also disrupt the formation of new stars, blowing away the very material needed for star birth. This dual role makes them both creators and destroyers in the cosmic landscape. Their rarity adds to their mystique. These stars are the cosmic equivalent of a once-in-a-lifetime event, making their impact all the more significant. In the grand tapestry of the universe, blue supergiants and hypergiants are the threads that weave together the stories of star birth, life, and death. As we wrap up our cosmic journey, let's recap the mind-blowing scale and rarity of blue supergiants and hypergiants. These aren't your average stars. They're the heavyweight champions of the universe, with some tipping the scales at over 100 times the mass of our Sun. Imagine, if you will, a star so massive that if it were placed where our Sun is, it would swallow up everything out to the orbit of Mars. That's not just big, that's astronomically enormous. These celestial giants are as rare as they are impressive. In our entire Milky Way galaxy, there are only a handful of true hypergiants. They're the VIPs of the stellar world, living fast and dying young in a cosmic blink of an eye. Their rarity and sheer size make them a sight to behold, even from millions of light years away. So, what's next on our stellar adventure? Stay tuned, because we're just getting started. In our next episode, we'll be diving into the mysterious world of neutron stars and black holes, the remnants of these massive stars. Trust me, you won't want to miss it. But for now, take a moment to gaze up at the night sky. Who knows? One of those tiny specks of light could be a blue supergiant or hypergiant, shining brightly against the vast expanse of space. Keep looking up, keep wondering, and until next time, stay curious.